Alright, I'm going to quickly go over the electroscope lab. I don't know how many of you guys take AP Physics 2, because I know you guys are into like AP Bio and whatever. But thought I'd do it because I know I have a few friends that actually take this class and need some help. So let's just start with the lab. So this is page 13. You rub a balloon on your head, and you want to see, or the question asks, draw how the charges would end up on the balloon and explain why. Hopefully you tried this whole thing before you watch this video, because the point is to actually try it out and learn something from this video instead of just copying out what I say. If we were to draw the balloon like so, you can imagine if I rub it like right here, the negative charge that it acquires is going to reside mainly there, right? That's where the charge is going to kind of reside. It's an insulator, so it's not going to like distribute itself. It's just going to stay there. And you could probably test this out, right? If you were to try to charge an electroscope on this spot, it probably won't do anything. You got to touch it right here. So just keep that in mind. It's an insulator. Which of the following would be impossible for the charge on your hair? So it basically, these are the options. It's going to list out, I think, negative 64 times 10 to the negative 19 coulombs, 64 times 10 to the negative 19 coulombs, 1.6 times 10 to the negative 20th coulombs, and then 32 times 10 to the negative 19 coulombs. Okay, you might be really tempted, if you're just doing this like without thinking, you might be really tempted to circle the first one, because it's like, hey, the balloon acquired a negative charge, but remember, we're talking about the hair. If they're both neutral to begin with, and you rub the balloon on your hair, if that gets a negative charge, your hair must have a net positive charge, right? And that makes sense. It's taking electrons away from your hair. So there's more protons than electrons, boom, positively charged hair. So it's got to be it's got to be these three. But remember, the fundamental unit of charge, we use the word E or the letter E sometimes for that, is equal to what is it equal to? 1.6 times 10 to the negative 19th coulomb. What that means, so that's the amount of charge on a proton, and the amount of charge on an electron would be negative 1.6 times 10 to the negative 19th. So if you, what this means is you can never have less than this amount of charge. If you have less than that amount of charge, that means you have less than an electron or less than a proton, and you gotta have at least one. You know what I mean? You know, if I have one excess proton, I have positive 1.6 times 10 to the 19 coulombs. If I have two, I multiply that by 2. If I do 3, so on and so forth. But you can never have a less than this, because you can never have a less than a proton. It can't be this one, right? Negative 20, bigger negative exponent number, or like, sorry, smaller exponent, smaller charge, negative 20 is less than negative 19. It's got to be these two. And you can actually test this out. If you were to divide these two numbers by this number, you would get, like, you wouldn't get any decimal, right? Because if you got a decimal, that would kind of mean that you have, like, for example, if I did this divided by that, that means I have, like, 1.2. If I got, like, 1.2, that means, like, you know, I have 1.2 lost electrons. That doesn't make sense, right? It would have to be a clean multiple. So let's go on to the electroscope part. Rub a balloon on your head and bring it close, but don't touch an electroscope. And I'm on the third kind of problem there. Draw what the charge would look like and explain why. Okay, so let's get our electroscope here. Remember, we haven't touched anything, so I know for sure my total electroscope has to be neutral, right? Why? Because if it weren't neutral, then if it did touch, then electrons can flow around and it won't end up being neutral. But because there's no touching, this stays neutral. But what's happening? Well, it's going to polarize. So an incorrect thing to really say is that protons move up closer because they're attracted to the negative charge here. What's really happening is there's going to be negative charges, electrons flowing down to the the bottom here. And if you have protons here, right? If you have protons here and you have negatives down here, you're going to have the same amount of negatives. I have 6 protons, or not 6 protons, but 6 positive charges here. To show neutrality, there would be like 6 here. It's still neutral, but it polarizes, and that's why you're going to get a little bit of deflection in your electroscope. And I know this electroscope's a little bit different. It actually looks more like this. So what's really going on is there's positives here, right? At the top, there's also negatives here, and then negatives on this part of the rod. So I'll draw a few more positives, and I'll draw some more negatives here. They're just causing a little bit of deflection because they repel. Boom. That's what's happening. Polarization, right? Induction polarization. Now bring the balloon away from the telescope. Well, now that you've kind of gotten rid of that sort of attraction, that attractive, or not attractive, sorry, because the positives aren't really being attracted away. It's more like the negatives being repelled. When you get rid of that repulsion, the negatives are just going to want to go back and redistribute. So you're going to get just a neutral electroscope that isn't like charged, like it isn't showing any deflection. So it would just look like this, right? So I would just draw kind of an equal amount of charge there. Cool? So now what happens, this one is an interesting one. Hold the charged balloon close to the electroscope, and while holding it there, touch the electroscope, and then bring your hand away and then the balloon. That sounds like some sort of like I don't know what that sounds like. It sounds like a whole complicated mess. What's going on when you do that? Well, let's take a look. So when we have our balloon and it has that negative charge, okay? So if I bring my electroscope, I know there's going to be more positives up here, and I'm just going to draw it like this. It's a bit easier to draw. More negatives here. But it's still neutral. Now, when I bring my hand, so pretend this is my hand. So I'll draw, I don't know, actually kind of looks like a foot, but whatever. Foot, sure, why not? If I bring whatever, and I'm touching it, well, it's a conductor, so electrons can flow now in between my hand and the electroscope. Well, they're not going to flow into the electroscope. Why? Because there's negatives kind of, there's negatives already here, and it's going to repel the negatives in my hand. These negatives and the negatives on this, electroscope are going to leave. They're going to jump off, and they're going to be like, hey, I don't want to be here anymore. So I can just draw these 4 headed over there, right? So now we have like these 4 positives and no more negatives. So, hey, if there's no more negatives down here, is it still going to be deflected? No. And if you actually try this, you could actually try this out. If you, in your lab, it'll stop deflecting when you start touching it. And this is kind of like grounding, right? We're grounding it, so that's not anything too crazy. But then when you take it away, when you take your hand away, then, sorry, you're not supposed to do that. I think you're supposed to take the balloon away. Wait, you're supposed to take the balloon away? Oh, no, yeah, you are supposed to bring the hand away. You're not supposed to bring the balloon away. I was like, wait, you're not, that wouldn't work. And I could talk about why. Take the hand away, and then you take the balloon away. So right now, if I take the hand away, this is pretty crazy. Is it going to be charged? No. Because there's no more electrons, well, there are, but not as many electrons down here. There's mainly positive down here. It's not actually going to be deflected. As soon as I take this away, guess what? Now, well, the positives aren't going to move around, but what's essentially going on is there's fewer electrons, and they're going to distribute around. And the way that they distribute is you end up getting positives, a net positive charge everywhere. So I'll just draw it like so. And if you're kind of confused by that, what basically is happening is when an electron So if let's say an electron, I have this eraser and an electron leaves that eraser. If one electron leaves, that's essentially one positive charge. Like that's the same as one positive charge. If two electrons leave, boom, you have like two, like a net positive, right? It's kind of like chemistry. I haven't taken chemistry yet, believe it or not. I'm actually taking it right now. But yeah, if two electrons leave, you get a positive here. That's kind of what's going on. The electrons down here would everything would distribute so that you would get a positive charge everywhere. Not the positives themselves, but it's just what's going on with the electrons. So, boom, you got that. You would get a positive charge. So now what we're going to do is just touch the electroscope. Hopefully this is pretty simple. When you touch it, so if I draw my hands, my fingernails here. So when I touch it, well, this time, instead of electrons leaving, electrons are going to kind of want to come back. They're going to join us here, and you get a neutral electroscope. I'm not going to draw that. I don't want to waste too much time. And I'm already at 11 minutes. I got to speed this up here. Recharge the balloon. We will assume that the balloon gets a charge of negative 10 Newton coulombs. Touch the electroscope with the charged balloon and draw what the charges look like. I'm getting kind of sick of redrawing these a bunch, but this is pretty straightforward. If you have your balloon and it's negatively charged, wait, did I draw negatives on my thing? I better have. Negative charges here. So if I'm touching, so wait, what am I doing? I'm going to touch the electroscope, which is initially neutral, and I won't necessarily draw those. Like I can draw, sure, positive, negative, whatever, right? I can draw an equal amount. But what happens is now when I touch it, guess what? Yeah, electrons are going to flow over. They're going to jump on over, and this whole thing will eventually get more negatives, right? And you will get a negative charge. And it looks kind of crazy, but boom. Yeah, that's really what's going on. Okay, which of the following could be possible charges for the balloon and electroscope? So the balloon initially had negative 10 Newton coulomb, or why did I say Newton? I'm sorry, nanocoulombs. That's nanocoulombs. That means a very small amount of charge. What could be possible charges for the balloon and electroscope? Well, your net. So I'm stammering way too much. Your charge is conserved, so your initial charge has to equal your final charge, right? We started off with negative 10 nanocoulombs. So at the end, let's say this has, I don't know, negative 2. This better have negative 8. If this has negative 9, the electroscope better have negative 1. The charge has to go somewhere so that the total equals negative 10. Now, how much distributes how much? Like, I don't know, like if they're the same size, maybe they'll have half and half, but this is also an insulator. I don't know. I would probably have to experiment and figure that out. But whatever options, I circled the 3 that add up to negative 10 to show that conservation of charge. All right, I'm going to do the post-lab, page 14, coming right up.